Very good evening. Good evening. Good evening. Good evening. Okay. So let's understand variance, bias, trade-off. Variance, bias, trade-off. Certain time, what happened? Our model starts learning the data in a different way. If I say, generally, the model learns the data points in a way in this way. So maximum data point learning the model is doing. But certain time what happens, the model does not behave in this way. It starts learning the data points on its own way. It means the model is not learning the actual data points which is provided. Model is making the self-assumptions of the best fit line. Okay, so it avoids the data points. So it starts learning the data on itself. It will be making self-assumption points on its own. Okay, so it means model is not learning the data properly. And whenever we are taking the new predictions, it is not able to predict the results well. This is the appropriate learning of the model, but certain time it is not learning properly all the data points. And certain time, if these are the data, the model starts learning all the data points. Even it is learning the noise as well. So it means these such situations occur in the case of bias variance trade-off. We call such situation where the model is not learning the data points well, that is making the self-assumption for all the data points. That is basically underfitting. This position is known as underfitting when model is making self-assumptions of all the points. And here, whenever model is learning all the data points, even it is learning the noise also. So here, it is not able to make the best fit line. So this situation is known as the overfitting. Underfitting and overfitting. So the point is that this situation can happen in the regressions as well as in classifications as well. So here, we can see here, the model is not learning any data points. Here also the model is not learning any data points. Here the model is learning everything. So all the situations are not properly. So here we can call this one as the underfitting. The model is making its self-assumption to learn the data points. And this situation we can call it a overfitting as well. This can be happening to the regression as well as in classification. So here also we can see this situation into classification is known as underfitting, as it is not able to predict the categories. Here this one is the appropriate position, but here the model is doing overfitting. So the point is here, underfitting or overfitting can happen even in regression or the classification. So basically these all are happening due to the due to the variance and bias present inside the model. So what happens certain time, if suppose here we say, if everything is fine, if we say there is no bias, no variance into the data, it means there is no underfit or no overfit into the data. Okay. If there is no underfit or overfit into the data, so it means everything is fine. So it means there's a low variance or low bias into the data. So all the learning points and the prediction points are onto the actual target. But at the same time, when there's a high bias present into the model, where the model starts learning on its self assumption points. So here, during the prediction, all the data points, all the new data predicted points are far away from the exact target. So if my target is this one, my target is this one. So here, the model starts predicting off the target if the model is having high bias. The same happens into the high variance, that whenever model should start predicting at the right target, but if the model is having a high variance, so in that case, all the predictions are coming nearby to the predicted point, but they are again with the high varied points it is predicting. And when the model is suffering from high bias and high variance, so here all the predictions are coming far away from the actual target, and all the data points which are coming far away, they are also highly varied. So this all happens due to the high predictions here. That is all already happening here. High variance and high bias. This all is happening just due to the underfitting and overfitting situations, or here underfitting and overfitting situations, which is coming into the regression as well as into the classifications as well. So here we do not need the high bias or the high variance. So in that case, we should know that if the high bias or high variance is there, so somewhere your errors are high. So we should try to reduce down the error at the optimal point. So we can just come down to the errors at the optimal points here. Okay, so this all happened due to the underfitting or overfitting. So here in these situations, we need to find out a solution through which we can come up with the problems of underfitting or overfitting here. So in that case, we can take, there are certain two techniques through which we can come up with the problem of bias variance trade-off, bias variance trade-off, or the problem of underfitting or overfitting. So those are basically here, wait, those are basically regularization technique, and cross-validation. Okay, regularization technique and the cross-validation here I'm having. These are the techniques through which we can remove the bias variance trade-off. Now let's come to the regularization. We are going to take all the things very step by step. So let's understand what is the regularization. In case of regularization, we try to minimize the error by using certain algorithm. So there are basically two techniques inside the regularization. So here, there's one of the technique is lasso, and one of the technique is ridge. We can call this lasso as L1. We can call this ridge as L2. So lasso regression and ridge regression is there. What happens in case of lasso? In case of lasso, there are coefficient values. Means here, if I'm having in a data set, X1 means variable, X2 variable, X3 variable, X4 variable. So a lasso regression, this is one of the algorithm which tries to omit or remove those variable coefficient values, they will try to reduce down the coefficient variable values to 0, those who are insignificant to the contribution of y. Okay, so in case of lasso, it will try to omit the coefficient values. It will try to omit the coefficient values to 0, so that this particular variable is insignificant to the contribution of y. This lasso works in this way. What ridge will do? Ridge will try to reduce down the gap between minimum and maximum difference of all the coefficient value. Because every variable here, every variable here, every variable has certain significant coefficient values. So some of the variables are having coefficient value in very high positive, and some of the variables are having the coefficient value with very negative as well. So negative coefficients and positive coefficients are there. So if some of the variables are having very high coefficient value, plus positive coefficient value, and some of the variables are having very less coefficient value, negative coefficient value. So ridge regression will try to reduce down the gap of the coefficient value. It will try to reduce down the gap of the coefficient values to minimum. So it will try to reduce down the gap. Right now, if I say, if these blue signs are there, so the gaps are too high into the positive coefficient and the negative coefficient. But in case of ridge regression, the gaps are ridge regression is trying to reduce the gaps between the regression. Here, it is trying to reduce down the gaps of this coefficient so that the gap could be come to the minimum level. With this case here, ridge regression tried to reduce down the error, and it will try to remove any kind of bias variance trade-off. In this case, it will try to make the coefficient value 0, or it will try to eliminate the particular variable by making it coefficient value completely 0. But here, ridge regression will try to make the gap, it will try to reduce the gap between the positive and the negative coefficient values here. So in this way, lasso and the ridge regression works to reduce down bias variance trade-off. Okay. These are done with the help of, there is one of the parameter inside lasso and the ridge regression, that is the alpha parameter. Alpha parameter. Alpha is one of the parameter whose values could be kept very low. And these values will be controlling down the omission of any variable or reducing down the coefficient values to 0. And the same, just to minimize the gap between the positive and the very negative coefficients of any variables. This all is done by the alpha values. Alpha is one of the parameter inside the lasso and the ridge regression. So here, if I'm writing here lasso, so here I can just pull up the values of alpha, and I can keep the value here 0.001, very least value I can change it here, either 0.001 or 0.001 in this way. 0.01 also, lower values we are going to keep it here, and it will start controlling all the coefficient values. The same here into the ridge regression also, we can use the alpha values such as 0.001, 0.001, 0.01 or 0.1. So we can keep very lower values of the alpha to reduce down the coefficient. We never keep the higher values. In a similar way, we are having one more regression here, regression technique through which we can control the bias variance trade-off. And that one is elastic net. In case of elastic net also, we can control both L1, L2, L1, L2. Okay. L1 and L2. So this elastic net will try to omit the variable as well as it will try to control the gap between the two coefficients as well. And it will do all these things internally. Internal controlling, it is doing everything. Okay, same elastic net also hold the alpha parameters here. So it will be holding the alpha parameter. So inside the alpha parameter here, we can keep a very lower value to see the resultants. So here basically in all the regularization technique, here we are having the alpha as the controlling signal through which we can control the values of lasso and the regression there. So for this, we are having regressions. So lasso regression, elastic net regression, and the ridge regressions we are having as one of the algorithm which are going to control everything internally. So here, we can see regularization in machine learning. By training in machine learning model, the model can easily be underfit or the overfit. To avoid this, we use the regularization in machine learning to properly fit a model to our test set here. Regularization techniques helps to reduce any kind of underfitting or overfitting to get the optimal model here. So we should avoid all these things here. So here we can have, you can see it here. Here you can see regularization. Regularization refers to techniques that use to calibrate machine learning model in order to minimize the adjusted loss functions and prevent any kind of underfitting and the overfitting here. Okay, regularization, we can fit our machine learning model appropriately on the given test set and hence reduce the errors in it here. The basic regularization techniques are ridge regression and the lasso regression, and there is elastic net regression also. So here I'm just taking one of the data set. Here I'm having load Boston data set. In the same data set, I'm going to add that code. So here I had already taken this load Boston data set, which is having a linear regression earlier. So this Boston data set, this one is the earlier data set, which we did it to predict the house prices here. This is the same case study, just we are adding certain more here. So these are the Boston keys, data, target, all the input variables, target is there. And so into the same file, we are adding it here. So here feature names, descriptions are given here. Here input and output variables are there. We are splitting out the data with a train test split here. Okay, we are checking out the shape and linear regression here we are using. Now the point is here, wait. Let me add a regularization here. So what happened? We try to keep a regularization just to minimize the error here. Okay. So here, how to use the regularization, you can see here. I'm just calling the from sklearn.linear model import lasso and the ridge regression. They are already inside the linear model here. Here, I'm going to call the lasso regression. So here, lasso regression, lasso, and here I'm making the instance of it. So only the internal working works there. Okay. So lasso regression here. I settle down the value of alpha with very lower value 0.001, 0.0001. And here I'm using the lasso regression to train and to predict the data here. Here we are checking out the mean squared error and the other matrix as well. So here I had tried one just to avoid the model should be not underfit or overfit. No case should be done here. Once we done it here, we can just take it out the mean squared error. The mean squared error should be reduced. Here, suppose here I had used a lasso regression. We can use the ridge regression also. Here we are just taking out the coefficient values. Some of the coefficient value, it will make it 0 completely. Here you can see ridge regression, how to use the ridge regression as well. We are using a ridge regression here, where I'm keeping the value of alpha 0.001. Here I'm using the ridge.fit, rd.fit, rd.score here, prediction and the matrix, we are checking it out. Okay. So these two, lasso and the ridge regression here I'm using, they will work internally and you can just take it out the mean squared error. The mean squared error should be reduced. Here, this one is the elastic net. Elastic net has the combination of both lasso and the ridge internally. Here we can use elastic net and the alpha value settled with a very lower value, 0.001 value. And we are just making the fit, prediction, score, and we are checking out the matrix as well. So here you can just check it out the mean squared error. So basically mean squared error means in all three algorithms, one can check it out how much mean squared error is reduced down. The model which is having very least mean squared error can be picked. But here one can do more thing just to improve the result. You can increase the alpha values. As what will happen here, you can see here alpha values could be these values, either this, not towards the higher value. If we are keeping the higher value, then it will reduce all the coefficients towards 0, means all the variables will be 0 there. So we do not need this. We want to give only few significant variable could be reduced, not everything. So here, here we do keep alpha value here to 0. So here, suppose here I had used 0.001. So here you can just check it out, the mean squared error here. And here this should be reduced. So suppose here, what you can try instead of this, another value. and you can stay with that value where you are having the least error here. So suppose here earlier the values we are using 0.001. If I want to improve the result to reduce down the error, we can use 0.001. This value we can use it. The same value I'm using it to the lasso, and the same value will be used here into alpha also. Here, this value should be given. This value should be given here. Okay. So means here above also 0.001 I'm using, in ridge also we are using here 0.001, and here also in elastic net also we should use the value of 0.001. This value we can use that instead of this 0.001 and we can run the code, we can just take it out how much errors is reduced. So we can keep eye on the error and we can see that the algorithm which is reducing the highest error, that should be picked. So here suppose even we can use instead of 0.001 so that the errors could be reduced more and more. So here you can use this values also 0.01 here. Instead of this alpha 0.01, if you're using a 0.01, so the same value could be used here also into ridge. Okay, this is there. Okay, so here you need to take the value here 0.01 and you can check out your results here like 0.01 and 0.01. So same value, need to keep it inside the lasso, inside the ridge and inside the elastic net. So all these three lasso regression or the ridge regression or the elastic net regression, they use is alpha value, the similar alpha value you can trace. Now you should not trace a bigger value, just like 1, 1, 5 or 10. Higher set value we should not use in case of alpha parameters because it will start minimizing all the variables. It will start zeroing all the variables. It will start minimizing all the variables. It will omit all the variables. So we should keep very small values here and we can see if the results are improved, the errors are less, so that we can pick it up. That particular point, that particular model, we can pick it up. And it will try to reduce your underfitting and overfitting. Yeah, it is better to run the regularization so that in any of the case, the model should not do any kind of underfitting or overfitting. It should be away from any kind of bias variance trade-off. This is the best technique. Okay. Now, here you can see, just like here, see, till now, like you had seen certain classifiers here, like you had seen about dysentery algorithm you have seen, or you have seen KNN, nearest neighbor, K nearest neighbor, decision tree, K nearest neighbor, decision tree here, and I feel neighbor, wait here, support vector machine. This algorithm you have seen. Till now you have seen here, these algorithm you are using for classification purpose. Like here you can see here, decision tree classifier. You had used a decision tree classifier for the classification purpose. You had used KNN classifier, you had used it. You had also used support vector classifier. Okay. Support vector classifier. So the point is here that we are having the classifications here. The same one I can use it for these decision tree KNN or SVM. I can use it for decision tree regressor also. Means here we can use this algorithm for the regression purpose also. KNN regressor. Support vector regressor. So we can use this algorithm for these purposes also. Classification as well as regression purposes here. Okay. So here I'm using these three algorithms also. One is here I'm using other algorithm onto the same data set. So here I'm using from sklearn.svm import SVR support vector regression. Here I'm using the code for SVR because inside the SVR there are kernels. Kernel is one of the parameter here. So inside the kernel, there are basic three kernels, linear, poly, and the RBF. So here I'm testing out the SVR with the kernel linear, making the data fit and predicted, and checking out the matrix here. Here I'm checking out the code for support vector regressor along with kernel poly. So I change the kernel poly. Here I'm making the training, testing, and the matrix as well. I'm checking out, and here I'm checking it out. SVR with kernel RBF and fit training method here I'm using, and errors also I'm checking it out. So the point is here, we can try out all the types of kernel into the support vector regressor to check it out here, a matrix as well. So we can check it out that which particular matrix is working, which particular kernel is working well with support vector regressor here. So here, this matrix are just coming with the linear case, kernel linear. This one is coming with the kernel poly. This one is just coming with the kernel RBF here. So here, if we check it out here, we can see this one is working well, where results are up and errors are also reduced. Okay, so it means kernel linear is working good for the support vector regressor. So here I'm testing the code individually, one by one. But we can do here in this way also. It means here, I can just use the code directly just by taking all the three different kernels into the list here, that we can take it here and we can pass it into the for loop. So this kernel list will be taking all the data here, which are into the list, and one by one, these values will be coming, such as support vector regressor kernel is equal to linear, support vector regressor kernel is equal to poly, support vector regressor kernel is equal to RBF. One by one, they will be coming. They will be taking it out, its fit, prediction, and the matrix here. So this one is for the kernel linear poly case. and the RBF case here. So the point is here, any of the way we can use it here just to test it out, all these different values here. You can read it, please. Can use that which particular algo with which particular kernel is working at the high score, as well as lowest error, low error, high score. Okay. The way like we are using a SVR, support vector regressor, in a similar way, we can find it out. Like sklearn, there is a KNN regressor. So sklearn.neighbors, k-neighbors regressor is there. So this one is there. Class sklearn.neighbors, k-neighbors regressor. So if we want to test out k-neighbors regressor, so we should take this k-neighbors regressor from here. We can just load from sklearn.neighbors, import k-neighbors regressor. And here, one can put it here from sklearn.neighbors, import k-neighbors regressor here, and you can use the entire fit, prediction, scoring, and checking out all the metrics with the help of k-neighbors regressor, and you can just check it out that which one is working well. SVR is better, k-neighbors is better. There is one more decision tree regressor, such as sklearn decision tree regressor. Decision tree regressor. Decision tree is there. So here you can take from sklearn.tree, import decision tree regressor. You can use it here just by making the instance of decision tree regressor. You can use fit, prediction, and then testing out the score as well as mean squared error. From there, one can check it out whether SVR is working well, k-neighbors regressor is working well, or decision tree regressor is working well. The point is here, there are many algorithms actually. So like here we are having linear regression, lasso, ridge, or elastic net, or regressors also we are having for the regression purposes here. Okay. So these are all regression related algos are there. Okay. So this one is a case of regularization. So such like, variance, bias, trade-off, regularization. There's another technique, cross-validation. Let's understand how this cross-validation works. Cross-validation also, this is a very popular technique. So here what we can do, see. When we talk about the cross-validation here, wait here. Whenever we are talking about the cross-validation, it means, let's say I'm having Okay, let's say, suppose I'm having a 500 rows. Let's consider a case I'm having a 500 rows. So I want to make a training and testing for 500 rows. So here, 0 to 100, 100 to 200, 200 to 300, 400, and 500. Basically, in case of cross-validation, entire data set, all the 500 rows will be rotated for the training as well as testing. Entire 500. Okay. So what happened in this case? Suppose I say first 0 to 100 rows, 100 to 200, 300, and 400. You see up to this data. 0 to 400 rows will go for the training. 0 to 400 rows will go for the training. And 400 to 500 rows will go for the testing. Okay. Now second, next time here 0 to 300 rows will go for the training and 400 to 500 rows will go for the training. The point is 0 to 300 and 400 to 500 will go for the training and 300 to 400 row will go for the testing. So you see how I am just making a 1-1 set moving towards the testing. Next time, up to here, training, and testing. Which row will go for testing? 200 to 300 row. Rest will go for the training, training and training. Okay. Okay. Training, testing, and this data is going for the training. I'll do it again. Just wait, please. Training. And the last time, again, this data is going for the testing. And the remaining is going for the training. Actually, now what is happening here? If we see, I had iterated entire data set for the purpose of testing. See this data. See this diagonal. This diagonal is moving towards the testing. Means entire 500 rows are moved one by one for the testing purpose. The point is here that the point is there. Actually, when we talk about the cross-validation, we need to iterate the entire data set for number of times. So here, how many number of times? So here we need to give CV, that how many number of times I want to iterate, and the iteration will be, suppose I'm saying 5 times I want to iterate the entire data set, because I'm having, let's say, 0 to 500 rows. So if I'm saying CV is equal to 5, so it means I want to make the iteration of entire data set in front of the model 5 times. So I will give the value of cross-validation with 5. So what will happen? What cross-validation will do? It will make 5 chunks of the entire data set, and it will start iterating. It will start rotating the data set in front of the model. So what will happen when the first round is there? Suppose here, the first round is there, CV is equal to 1. So here, 0 to 400 rows will go for the training, and 400 to 500 will go for the testing. Second time, 0 to 300 and 400 to 500 values will go for the training. Rest will go for the testing here. Here, 200 to 300 will go for the testing. And here, this will go with the 3rd round. Here, it will go for the 4th round. Here, it will go for the 5th round. So the point is here, with every cross-validation round, one of the chunk is moving in front of testing, rest of the data is moving into the training. So just wait here. Here, let me create it. Wait. Suppose here I'm saying again, let's take an easy one. I'm having total number of rows, 300. I want to iterate these 300 rows with 3 rounds. So I had taken cross-validation value of 3. Now let me make it here. So here I'm making it 3 round, it will be making 3 round cross-validation technique will be making. So here 300 rows, so 3 round it will be making. So here I'm making 3 chunks. I'm dividing the entire data set into 3 chunks. 0 to 100, 100 to 200, 200 to 300. So here, in the first round, when CV is equal to 1, these 0 to 200 data will be moving for the training, and 200 to 300 row will be moving for the testing into the first round when cross-validation is equal to 1. So when the data is moving for the training and testing, we will be getting certain accuracy score. So some accuracy score we are getting into the first round, this first round. So let's say, suppose I'm having accuracy score of 0.85. we are getting into the first round. Done. Now let's go to the second round here. So here, when cross-validation is equal to 2, so which data is moving towards the training and testing? So here, this data, 0 to 100 data will be moving for the training. 200 to 300 data will be moving for the training. And 100 to 200 data will be moving for the testing. Now into the third round. See, in third round, 0 to 200 rows are moving for the testing. 100 to 300 rows are moving for the training here. Here, you consider, suppose, in round number 2, you are getting an accuracy of 0.90. And here, in round number 3, we are getting an accuracy of 1.0. Let's assume. So here, accuracy scores are coming with each and every round, each and every rotation, because we are sending entire data set in front of model. So that model can see all the values with the help of training and testing, with the help of all the cross-validation rounds. So the accuracy score which we are getting here in different rounds, its mean is find it out. So its mean is actual accuracy score. Mean is actual accuracy score. So this is the mean. So this mean is actual accuracy score. Okay. So this is there. So in this way, your cross-validation works. Even if you take, suppose here, suppose here, I'm having 1000 rows. So here I'm giving the CV is equal to 10. So what will happen? The data set will be divided into 10 chunks. It will be dividing the rows into the 10 chunks, so that all the 10 chunks should be iterated or rotated in front of the model one by one. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 0 to 1000 it is going to iterate. So 10, 100, you can take 100, 200, 300. And entire data set will find out the turn for iteration, and all the values will be iterated in front of the model during the training and testing. So here I can say like n is equal to 1, first round, second round, third round, fourth round. Okay, they all will go up to n is equal to 10. And these values, I say like entire data set, all the chunks will be iterated one by one with the testing. And rest of the values will be moving for the training. Okay, so training and training. Okay, training and training. The point is here, entire values are moving for the testing and the training here. So here n is equal to 1, 2, 3, 4, 5, up to 10 here. Now you need to take all the accuracy which is coming here here, here, with all the 10 accuracy. So here one needs to find out the mean. So that is the actual accuracy. Mean accuracy is the actual accuracy. So in this way, your cross-validation work. The point is of the cross-validation is the entire data set, all values are iterated in front of the model so that whenever we are giving the new data, new predicted data, it will be answering better. It will be predicting more better answers without any bias variances here. So when we talk about the cross-validation, so this is a basic cross-validation here. So when we talk about the cross-validation here, basically, there are 3 types of cross-validation, basic. Like one is hold-out cross-validation. Hold-out cross-validation is the same, which we can say when we divide the data into 80% or 20%. That was the default cross-validation, basically. We do the train test split. So we do there, either the data are split with 70-20%, or either the data are split with 80-20%. That is there. Second, cross-validation. This one is the actual cross-validation. The cross-validation I had explained to you right now. That was actual cross-validation. There is one more. This cross-validation is named as a K-fold cross-validation. We call it a K-fold cross-validation. There is one more cross-validation, that is leave one out cross-validation. Leave one out cross-validation. So this one is the default one which we are already using with the train test wave. K-fold cross-validation, which I had shown you right now. So what is K here? K is a CV here. Like here I'm writing CV is equal to 5. We can write here K is equal to 5 also. That's all. The same is there. The number of cross-validation numbers, these are there. Leave one out cross-validation. Leave one out as cross-validation is nobody uses it actually, but it is there. Somebody has created, so that is there. Leave one out cross-validation in this case, I'll tell you, just wait here. But it is nobody uses because there is no much use of this one, not a better one. So we do prefer K-fold cross-validation here. Let's see how we can work with K-fold cross-validation here. Types of cross-validation. There's a hold-out cross-validation. You can see here, hold-out cross-validation is the same here. You can see this one is a hold-out cross-validation. Hold-out cross-validation is the same one, where training data you are splitting with the 70 or validation data you are giving it 30%. Validation means you are testing data, or you are giving it with the 80 or 20 also, that you are doing it. K-fold cross-validation, this you can see it here. This one is the same which I had told you. Let me explain it. This one is a leave one out. Wait here. I'll tell you. Let me come to the practical here. Okay, so for this cross validation, you can see here, I just use the iris dataset currently here. So this is the same dataset which I had used earlier also. Here, just we are adding some code only for the cross validation here. So iris dataset already we are taking it here. So here, like we had used multinomial NB, support vector classifier, decision tree classifier, neighbor, K neighbors classifier also we had used it here. Matrix also we had called. So here I'm loading them using the same data set. And all the algorithms which we had used earlier, this is the same. This is the same here. So we'll be adding some more code for the cross validation here. Here, this one is like X-train, X-test. We are doing it here. We are making a train test. This one is a holdout cross validation, which is a default one. Here we had used a multinomial NB. Support vector classifier, we are using it here. Decision tree classifier, we are using it here. These are the all earlier algos which we had worked here earlier. Now what we can do, once we had used all these algo, now we have to add the code for cross-val score. Cross-val score here, we can add it here. Here, LOCV, actually, that is very rarely used because that is no use of it, actually. And rarely we do have very small data set, actually. We do not work onto the very small data set. We have a large data set. So there we do work cross-validation, K-fold cross-val, okay? But actually, the reason is there are so many research into the world. They keep on creating certain new algos. So one of them has given this LOOCV, but we never used it. Yeah. Okay, so here you can see, like here, see this is the old code here, old code. Here I'm using the cross validation. So we need to apply the cross validation on the existing classifiers, on the existing classifier, such as MNB, because here we can see like we had already worked onto the MNB. So here MNB instances there. Here we are having an instance of SVC. These instances we are having. Here we are having the instances of DTC, KNN. So all instances are there. So here, we are adding a cross-val score on the same MNB. So here you can see, I'm just using it so that we can iterate, we can rotate the entire data set in front of the model so that there could be no kind of any underfitting or overfitting can be happened. It should avoid it. So here we are calling it cross-val score. These are predefined libraries. From sklearn.model selection, it is present here. From sklearn.model selection, import cross-val score. Okay, cross-val score here I'm calling. Here I need to call inside the, whenever I'm using a cross-val score, here, I need to call here classifier. Classifier. It could be any model name. Any model name. Okay. Then here I need to give entire input, entire output, because cross-val score will take all the input and output, and it will take all the decision on its own to make the different chunks of the data. It will make itself internally, X-train and Y-train internally, because it will rotate entire data set in front of model. Okay. Then here we can give the value that how many rotation we need. So CV cross validation here. So suppose that I'm saying CV5. So basically, even in cross-val score, CV is equal to 5 means 5 rotation it will mean. So the point is here, 5 rotation means 5 rotation means 5 iteration it will make. 5 iteration it will make. Okay. CV is equal to 5, so 5 iteration it will make it. It is defaulting. This CV is equal to 5 means 5 chunks it will make, and it will take 5 rounds to rotate all the chunks in front of the model here. So here I'm doing it, cross-val score here, I'm calling it here. We need to pass out the model. So model name is MNB. So we are making the cross-validation of the MNB model, multinomial naive Bayes here. I'm using it here. I'm sending out the X and Y completely, which is the input data and the output data of load iris. Here I'm making the cross-validation of Y. This will return us the score. Score means accuracy it will be returning. And here we can just check it out, the score. These are the different scores coming here. And we can find out the mean as well as the standard deviation. So this one is the mean. Mean is the total accuracy score, which is 0.95. Okay, so that is there. So here, suppose here these are CV is equal to 5. Think it, CV is equal to 5 is there. And here, I had divided the data set into the 5 chunks now. So CV is equal to 5 I had 10. So here 5 chunks will be created automatically. Means here there are as many as number of rows, so automatically 5 chunks it will be created. And it will be sending these chunks one by one to the training and testing. So these values are rotating for the testing, and the rest of the values are going for the training. These values are going for the train and train. So here's 0, 100, 200, 300, 400. When we are getting a value of cross-validation 1, so here we'll be getting an accuracy score. So what accuracy into the first round we are getting? When training and testing data is moving, what accuracy we are getting? That we are getting, suppose here it is giving 1. So this score is coming here, print score, this one is a 1. So here 1 is the accuracy. Next, this one is the accuracy here. For the second round, 0.96 is the accuracy for the second round. 0.9 is the accuracy for the third round. 0.9 is the accuracy for the fourth round. And 1.0 is the accuracy for fourth round here. Okay. Okay. So these are the various accuracies coming here, individual accuracies with individual round. So here we can find out the mean. So here the entire mean is find it out. Mean is find it out. So here one is finding out the score dot mean. So this one is the entire means in 95. So the point is here we are getting a highest value 1. 1 means 100%. So it means in this entire data set, when the model is making the training and testing, so at one time it has reached to 1 also. It means your model is doing very well. Even 2 times here. So it means model is predicting very well. So it is avoiding entire kind of underfitting or overfitting. Okay. So 0.95 is the accuracy coming as the mean. And there is very less standard deviation. So 0.95, it means I will say 95% my model is working in case of cross-validation with M and B. The similar way I can test it out, this cross-val score for the both KNN and the DTC also. Because above you can see above, I had created a KNN model also, entire training test above also I did it. And I had, there is a DTC also, you know, about DTC I had created there. Okay. Okay, just wait here. So here, like KNN, KNN is there. So I'm using a KNN which is created above. Above I had created, here I had created. KNN I had created over here. KNN, this is KNN and DTC. These two I had created. So I'm using the same these instances I'm using for the cross-validation purpose. Okay, so here I'm using a KNN and here I'm using a DTC. So this one is again, we are sending it out the model name, input and the output CV. So mean value and standard deviation, it is coming here, 0.97. In DTC here, mean value and the standard deviation is coming here, 0.95. And the, this standard deviation is coming here. So we need to check it out the mean value every time, mean value every time. Okay, these scores are individual score of all 5 terms here, just like 0.96, 96%, 96%, 90%, 93%, 1.0, 100%. So, but here we need to find out the mean of cross-validation. So if we check it out here, from here, so see, DTC is giving us result 95%. KNN is giving here 97%. This is good. Any other? SPC. This one is, okay, let me tell you this also. Generally, when we call about the cross-validation, we call it a K-fold cross-validation. We call it a K-fold cross-validation, okay? And see, either you write a code, cross-val score, and here you are passing out the model name. That could be any model name. Here you are passing out input, output, and here you are writing CV is equal to 5, or you can write CV is equal to 10, or you can write CV is equal to 15, or CV is equal to 7, you can write it. Just you can take these and just to see what is the result. If you want to improve the result, you can improve the CV is equal to 10, 15, 7, 8, 11 also you can do that. Just you need to come up with a cross-validation mean, this one. Here, now if I talk about the K-fold, so this value which is I'm taking with the CV, this can be changed with K-fold, this one. From sklearn.model selection, import kfold. From sklearn.model selection, import kfold. Okay. So we can write in this way. See, this kfold, how can I write it? Means student, you can give CV also, or you can give a kfold. Both are same, no matter. So here I'm using a kfold. So here basically now kfold number of split is a parameter. Kfold is one of the class. N split is basically here. Suppose here number of split. How many split I want to give? This then you can give 5, 7, 12. Anything you can give it, but the results could be upside. Here I'm making the instance of that. Okay. Now this value, kfold, which is holding the value of 5. This kfold instance could be passed here inside the CV. You can use this, you can use this, anything. This one is the N split here, number of split. So Crosswell score, model name, input, output, CV is equal to kfold. Okay. Okay. You can use any. See, either kfold is also okay or CV, anything you can use it. Okay. So this is there. Now we can see that which one is performing good. Suppose here I say, wait, let me check it out. Here DTC, wait, we can make a table also. Suppose here I say DTC, this is giving me result of 95. DTC here result of 95. So 0.95, I mean 95% working here with the cross validation. KNN is working 0.97. KNN is working 0.97. This one is SVC. SVC is working 0.93. MNP 0.95. So we can choose any one of them, means which is working the best one here. Okay, so suppose that KNN is on the top with the cross validation, we can take that. So here we can save that particular model which is working on the highest one. So you can save that particular model. So here, suppose I say KNN 0.97 is taking. So here we can take that particular. So import joblib.dump. So here you can use KNN. Here you can use KNN. Instead of DTC, I can use KNN. You can give the name here of the file and we can dump it. So this particular KNN model is saved with a particular name, the name which we are passing it here as an object file. The model will be saved. And if we are using load method, so this particular file, the name which we had saved, that will be back and we can use it we can use it for the prediction purpose. Okay, so this is one. I can use a joblib or I can use the pickle method also. So into the pickle method, just you can name the file, take the model which you want to save, which is on to the highest level, that model instance. You can open the file into the right binary mod here. Okay, so the file will be saved with pickle file.obj And if you want to read it back, you can read it. You can open the pickle.load, open the file name into the read binary mode, and you can predict it with the new result here. Right? Here now, so in this way, means here, you need to take the entire data set, do the entire EDA, do the feature engineering, then take the model, apply various model, avoid any kind of underfitting or overfitting, use the cross-validation or regressions in case of regression files, regression databases, otherwise here into the classification basis, use the cross-validation and see which one is working on the highest level. That model you can save it. Okay. There is one more, leave one out, means here, when we had talked about cross-validation, when we are talking about the cross-validation. So here, like I told you, 3 basic types are there. One is a holdout. Holdout is a 80% and 20% is there. Second one is k-fold cross-validation. And the third one is leave one out cross-validation. Leave one out cross-validation. So leave one out. Now what it will do, leave one out. It's not used anywhere else. See, leave one out will leave one row for testing. Suppose I'm having 0, 1, 2, 3, 4, 5, 6, 7. Suppose here 0 to 100 rows I'm having. What leave one out cross-validation will do? It will just pick 90, it will pick 100 row, and this will be sent to the testing, and rest 99 will send to the training. Next time, this 99th row only that will go for the testing, rest rows will be going for the training. So it means how much time it will take? If I'm having 1000 rows, I'm having 5000 rows because data sets are larger. So one row only going for the testing, rest are going for the training. So the point is there that it's not very convenient because one row is going. So we don't use it generally. Generally, I never used it. But it is there. So as a knowledge purpose, you should know. So from sklearn.model selection, leave one out is there. One is making it here, but don't use it. There's no use of it. Why to use it? Only one row is going for the testing here. The best is k-fold cross-validation. You can use that. So just here we are using a cross-val score, k-fold cross-validation. You can give the CV is equal to, by default, the CV is equal to 5, default here. But what you can do, you can increase it. Suppose you can increase CV is equal to 7. Try it. CV is equal to 10, you are using it here. So you can just improve this particular mean score. So if here you are using CV5, so you can try with CV10, just wait. If here all the defaults are CV5, so you can give CV7. Try it in all others, other also cross-val score you are using with other algos. So CV is equal to 7, you can try and see whether you are improving with this one. If not, so what you can do, CV is equal to 10, CV is equal to 10, you can use it. And the same CV is equal to 10, you can use, means 10 chunks, 10 times iteration, 10 times rotation you are demanding. So CV is equal to 10, you can go ahead with others also. Means there are 2, 3, 4, 5 algorithms I have used. So they are also CV is equal to 10. Run all and just to see whether you are improving with it. And stay with that particular algo and CV where you are getting the highest one. In this way, you can do that. Okay. This is a cross validation. These all techniques are used just to avoid any kind of underfitting or overfitting, variance bias trade-off. Here, this file, SVC prediction.csv, this is nothing. I'm just saving the result only. There's nothing I'm doing. You will never find any file anywhere, this one. So this one is because when I had predicted some data, somewhere predict SVC, maybe I had given. Here I had, during the prediction, I had given predict SVC. Predict SVC I had given. Predict SVC. The same if I want to store it into the data frame. So df1.2csv, I'm just storing it SVC prediction.csv. Means here the predicted data I want to save it as a CSV. You can find out this file into the home page. There you can find it out. If you are doing it, you are working it, you are saving it, your predicted data. So you will be finding it out, that data into the home page. Okay, you will be finding it out. You will not find it out into the GitHub because this is a predicted data save. This is not a data set anywhere. Okay, got the point? Rest you can write the code. You have to write the code on your own. That is much better here. Here I had took the entire example. This is the same code which I had written earlier. This is the same code which I had written earlier. This is the same earlier file which I had used it. Just only few more codes I had added. You have to practice and write the code on your own. This is the same file. All these things I had written earlier, the file which you will be creating earlier. You can use the same file. You need to open the file, the previous file you had worked for the entire classification. Same file you have to open, same file you have to run all, and just you need the add code for the cross-val score. These are the same code which we were using earlier. I had written all the code earlier. So whenever you are writing, the same file you need to open, earlier file you need to open, run all, and add further code into the existing file. I had already explained the entire file here. Okay, you can see here. I had explained the entire file here in details. Okay, certain time what happens, see, currently we are using a classifier differently. Means here we are using a decision tree classifier, support vector classifier, k-neighbors classifier, multinomial NB or any other algorithms. So currently we are doing it, testing it out separately in a separate code also. Okay, but what we can do it here, we can just conclude entire code and I can put it inside the for loop and the entire code iteration could be done on the basis of training, testing, and then checking out the metrics as well. So here I'm just using them all. Like here, decision tree classifier. Suppose here I'm just creating various instances. Like here, DTC, these, we are various instances. I'm creating it here, putting all the instances here into the model here. For model, M in model. Here I'm using, so one by one, what will happen inside the model, DTC will come here, DTC.fit, score, DTC.predict, support vector classifier.fit.score prediction, and the accuracy means matrix. Then KNN will be iterated, then MNB will be iterated, and checking it out all the training, testing, and the matrix as well. This also we can do it at a once, means in a one code, single code, we can do that. So here, these are the results coming for decision tree classifier. These are the results which are coming for support vector classifier. And these are the results which are coming for the key neighbors classifier. These are the results which are coming for the MNP. So here in this way also we can write the code. Actually here, there are in support vector classifier, in support vector classifier, there is a kernel. I told you earlier also, support vector classifier or regressor. So basically support vector R or support vector C, there's a kernel parameter which is having basic three value, either the linear, poly, or RBF, poly or radial basis function. These are all mathematical values. They are running certain mathematical code inside it. Mathematical expressions are working. They are working for the better learning of the model, even with the regression or with the classification. So what we can do whenever we are trying these codes, so suppose that I'm using support vector regressor. So we can try that if I'm using a kernel linear, and then I'm using this particular sv.fit, I'm using sv.predict, I'm using, or with this SVR linear, so, or I'm using any matrix, just I'm using mean squared error or R square, we are checking it out. So we can check it out that what are the values coming here for the MSC or R square with the kernel linear in case of SVR. This is one case. If I want to see, like instead of linear, I want to use a poly. So let's see with poly what results we are making, or even if I'm using the RBF, so with RBF kernel, what results we are making. So actually we do use all the values of kernel differently and checking it out what matrix we are getting. So we'll be taking that value where we are getting the best matrix with a lower mean squared error and with a higher R square. So the point is here, these kernels like linear, poly, RBF, again, mathematical formulas are working internally. They are just working to give the best learning of the model for any particular data set. So actually we keep trying these things and try to find out the best result, that which particular mathematical model learns best the particular data set. So that's why we take a single data set and we apply number of algorithms onto the particular data set so that we can check it out, that because in every algo or every model, some mathematical models are working. They are having the Python code that we are using. So those all mathematical models which are working internally, they try to grasp the data and try to frame its self-manipulation, the way the mathematical formulas are written. And there they learn, they fit, they predict, they put the square error, mean square error, or accuracy score, your classification report, other things, means matrix related with the classification, matrix related with the regression also. So from there, we can choose out that which particular model is able to grasp, to learn the data set well, to predict the data set well. That is the overall learning of the machine learning, basically. Okay. So that one is about the cross-validation here. Here, wait, let me check it out. These are the earlier files I'm using. Okay, here, now let's go ahead with certain scaling techniques. Certain time what happens, suppose, let's say, I'm having a data set. Inside the data set, I'm having a gender, let's say age, let's take a salary. Inside the gender, if let's say I'm having a value of M, F, F, M, M, F, in this way I'm having. Okay, we use the label encoder here and we transform the value towards 0, 1. Like 0, 1, 1, 0, 0, 1 means label encoder, you can use it. Now let's come to, it means my genders are transformed towards the 0, 1, 0, 1. My genders are transformed towards the these values with the help of label encoder, means integral value, numeric values, they are changed. Let's come to the age now. Age could be any age. Let's say I'm saying 25 age, 32 age, 35 age, 45 age, 40, any age I'm talking about. Now, in the salary, okay, suppose I say salary is coming into the float data. Here it is integer, here it is integer, here it is coming into the float data. So suppose salary is I want to say the salary structures are very different. Some are getting low, some are getting very high, some are getting medium salaries. So the point is here, the format means here you can see, here my data, which is coming in numeric, they are into the form of unit. Unit means 0101. Here the data which is coming into the age, they are with tens, means unit tens, means here the data is into the 2 figure. Here the data are into one figure. Here I'm having the data into 2 figure. In salaries, I'm having the values of salaries with some lower values with certain higher values. And here the data I'm getting into the float data. So if you see the ranges of the salaries, so salaries are moving up to lakhs. Here I'm having the data up to tens, here lakhs, here unit only. So there is a quite big difference into the scale I'm talking about, scaling. So what happened, even we can give this data to the model will learn and will give predictions, okay. But still we can give a better data. So we can give a scaled data. So scaling, we can do it here. Okay. So basically now there are scaling techniques. We use scaling techniques to scale all the data in a one format. Instead of different like unit, tens and lakhs are coming, we can scale the data in a different formats here. So there is a certain scale, such as standard scaler. Standard scaler, here we can use it. What happened in standard scaler? All the data will be, in case of standard scaler, all the data will be having a value of mean 0 and standard deviation 1. So the point is here, standard scaling will be making all the data with mean value 0 and standard deviation plus minus 1. So it means all the predicted values are between here and here, means plus 1 and minus 1. Okay. So all the data is scaled into one format where mean is equal to 0 and standard deviation is equal to 1. Here, in case of gender, I had told you the best approach is use the label encoder. Though it is correct, you can use the one-hot encoder also, that is right. Because we are having 2 values only, MF that we are having. But I will suggest to you, that is a suggestion, you take a label encoder. Maybe a third values are coming, I don't know, in this way. So I'll say that when you use the categorical encoder you are using now, whenever you are transforming category data into numerical data now, the best approach is use the label encoder. It is suggestible, but you can use the one-hot encoder also because MF values are there. But certain time, if my databases are, suppose I say my data sets are 3,000, 4,000, maybe there are certain another third value is there in between. Maybe I'm not able to trace. So it is, I just directly use the label encoder so that if values are there, so 0, 1, 2, 3 in this way it will come in. That is a suggestion, you can take it. Okay, let's go to the scaling here. So if I make all the values scaled, so entire data set will be scaled into 1 and its mean will become 0 and standard deviation will become 1. Because if I'm providing a data set to the model in a learning where my mean is equal to 0 and standard deviation is equal to 1. So whenever I make a prediction, so during the prediction, I will be getting all the data within the plus minus 1 zone only. So predictions will be nearby. It is much better. This is one of the standard scaler. So for that, I'm having a technique, standard scaling. So we can call that. So currently what I can do, see, here I'm using the older data set, which I had already worked. That one is logistic regression here I'm using. already we had worked. Actually, we are applying all this technique into the pre-existing files only. So I just took the earlier files, where I had used the cancer detection work during the logistic regression. We did it. This is the same file here. I'm using it. So same file, it is nothing here. I had used the logistic regression. I had load the cancer data. It is into logistic regression here. Cancer set.keys, cancer set.values. There's nothing changed here. These are all the same code, whichever I had written earlier. These are the same code, nothing. So it means if you had prepared your file, the same file, you can open that cancer detection file, click on cell, click on run all. Your file will be updated into the Jupyter. These are the same file where 01011 is to make the cancer prediction. Here, keys, target name, data, shape, or everything is there. This is the same, no code new is there. Earlier code I'm running, which I had written in front of you. These are the same code. I'm predicting a file. Okay, just wait, see. If you see this file, let's see its data first, okay? This one is the original file. So if I see this file here, you can see let it be any column, but you see the values, 17.99, 20.57. You see this value, it is coming up to unit tens. Here it is coming into the 100, 122, 132, 130. Here it is coming into thousands. Here it is coming only 0 point decimals. See this value. See this value. Here I used the same data set to the logistic regression. Let me check it out the value into the accuracy score. Accuracy is coming 0.93. And if we check it out, the precision recall also, different values are there. But average accuracy is coming 0.94, means 94% general I'm talking about. Okay. So with logistic regression, with the original data set, nearby 94% accuracy is coming. Now let me try out the scaling data. So here I'm just coming with the scaling data. Scaling techniques I'm going to use it, where I'm going to use the standard scaling. With the standard scaling here, you can see the formula, how the standard scaling works internally. X minus mean divided by standard deviation, the value which we are receiving, that one is the standard value. Okay, with the help of standard scaling. So here I'm just calling the standard scaler. Again, all the libraries are there. I'm going to use it directly from sklearn.preprocessing import standard scaler. The point is here, I'm trying that in logistic regression, I took the actual data set, original data set, and put the data into the logistic regression for training and testing. Now, instead of putting the original data set, I want to scale the data set better. And then I will put it into the any model here. So here I'll just taking the data set. So what I'm doing, I just took the value of all the input data. So you can see here from sklearn.preprocessing import standard scaler. Standard scaler instance I had created, st.fit_transform, and here I had passed the input data. So that the entire input data should be one scaled only, where mean will become 0 and standard deviation will be becoming 1. So it means there is no variation much into the data. Okay, so data could be same scaled. So if you see this data here, st.fit_transform x is there. Here you can see these values. standard scalar. I made the instance. I just put X into the st.fit_transform, X is there. So this one is the scaled data. You can see all the values. See these values, all are coming into the same scale. Same format is there. Okay. Here, I'm just taking the entire data inside the data frame here. So this one is the data. See here. You can see all the data is coming into the same scale. Scale, you can see it here. All the data is coming into the same scale with the standard scalar. Earlier, this data is not coming into the same scale. See, this one is original. This scale is different. And after making the same scale here, see this one. See this data. This one is the, see this one is the same scale data with the help of standard scalar. Now we'll be sending out these values. Here it is saying x dot mean. So this one is a 0. And here standard deviation is plus minus 1. So 0 mean and standard deviation 1. Now here I'm taking this X data. This one is a scaled data. Here this X data here I'm taking into the train test split. This one is a scaled data. And Y here I'm doing it. X, Y I'm doing it here. And now the new data which I had given, this one is into the logistic regression I'm giving to it. And here, let's see the accuracy score. The accuracy score is coming here with 98. Earlier, when I'm directly using the logistic regression with the original data set, there I'm getting 93, but here I'm using 98. Here I'm getting 98 with the scaled data. This one is coming with the scaled data. Here, because I am passing the scaled data. So here it means my accuracy is coming here with scaled data 98. So it means it is improvement with the scaled data. Okay, if I'm giving the scale data, it is improved here. Got the point? Here also you can see the F1 score. You can see the other values of precision and recall also. They are improved as per the logistic regression with original data set. So if we are passing out the scaled data, so that is much better for the learning to the model and the prediction as well. Your score will be improved in any of the cases here. Okay, so that is way. Now, I can do, there is one more technique here. This value, we are just checking it out. Let's go ahead with the min max scalar. What is this? I can use this also. This is also another technique, min max scalar. That is, see, generally what happens, suppose here I'm saying salary. Let's take a salary. Let's take a salary. Suppose anybody is getting 220 wage as a wages. One is getting 2,000 as a wages. One is getting 2 lakh as the wages. See the difference into the salary. One is very lower, mediocre, and higher side. The point is here, there is a quite a gap, difference inside the column data. So again, it is not scaled. So what I can use, there is another scaling technique. We can give it, that one is a min max scalar. Inside the min max scalar, 0, what happened if I'm using a min max scalar, the minimum value will be 0 and the maximum value will be 1. Minimum values will be 0, maximum value will be 1. So entire data will be moving between the values of 0 and 1. 0 and 1 means internal values, decimal values it will be having. So this technique also we can use it to make the entire data set scaled. So there is a min-max scalar also as a scaling technique. So 2 techniques are there. Scaling technique means standard scalar, where mean is 0, standard deviation is 1. And the another one is a min-max scalar. Inside the min-max scalar here, here you can see the formula. The data point minus the minimum point inside that particular data set and divided by the maximum point minus the minimum point. That would be the min-max scalar. So here I'm using from sklearn.preprocessing import min-max scalar, making the instance of it, giving the input data x inside the min-max scalar and taking out the value. You can see the value, what values I'm getting. See this value carefully here. I'm getting a value because I told the minimum value 0 and the maximum value 1 I will be getting in case of min-max scalar. You can see all the values are in 0.52, 0.02, 0.54, 0.91, 0.59, 0.23, 0.63, 0.27, 0.22, 0.21, 0.39, and all these things. Means all the values are iterating among here, 0 and 1, 0 and 1, 0 and 1. Here I'm just looking all the data into the data frame. See all the values which are iterating between decimal values. Okay. Now I will be using this X. Here I'm using this X, using the logistic regression to fit the new X. So here also I'm getting 0.98. Okay, so the point is here 0.98245. Okay, 0.98245 as an accuracy. And here also 0.98245. The point is here almost both are working same. It means scaling techniques, that one is standard scaling or min-max scaling. Both are working good. They are reaching to the 98 instead of original data set. So it is better to use scaling techniques also. Got the point? To get the good results, best predictions. Either scaling techniques also or min-max scalar. Okay, so we can see that which one is giving the good, the original only or scaling. With scaling, we can upgrade our results. So that could be done. You can see here which the data set which I had used for the Abalon data set. You can see it here. Last time also I discussed it. I just called the label encoder also here. Inside this file, label encoder I had called, standard scalar also I had called it here. Okay. And here I had used all these things yesterday also. I had told you this file. But let me show you here label encoder I had used. This is the earlier file yesterday I discussed it. Here you can see label encoder because inside this data set, oh, see this one. There is one of the column here. Why I had taken 0? Because if you see the data set, inside the data set, the 0th index, this index you can see. This index, this one is 0, 1, 2, 3, 4, 5, 6, goes on. So here, gender is 0th index. So I need to capture this index. So how can I take it here? df.ilog, take all the rows and the 0th index. That one can take it as the, any variable you can take it here. So 0th index, I'm taking it here because these are coming into the MF. But you see here one more thing, why I'm saying the label encoder. See here, male, female, I is also there as an infant. So third value. So here, if I apply one hot encoder, that will not work. That will throw the error because one hot encoder will be taking the value 0 on. So that's why I'm saying in case of gender means here the best way is use the label encoder because you can get the value 0, 1, 2, 3. So here male, female, I, infant means small baby, 1 month, 2 months, 3 months, they are infants actually. So here 0, 1, 2 values will be going. Suppose here M is going 0, F is having 1. So infant, child, small baby. So that is getting the two values actually. So I'll suggest you to use the label encoder. Rest is up to you. Here, somewhere I wait. Okay, see here. First, I had grabbed this variable df.ilog. I checked it out. The 0th index is having the gender. Nearby 4,176 values are there. Rows are there. I took the label encoder. LAN code is the instance. LAN code.fit underscore transform. With there, I had passed the data frame name and the column name, which is a gender here. I had passed it here. And this one is the updated gender. So this gender, if I'm checking it out, that one is coming into 0, 1, 2 values. So categorical values are transformed into the numerical values. And now my data set have the value. You can see these values here. These values. Okay, so in this way we can do that. And once we do the entire EDA process, we did it. Entire EDA process, I did it. I clean the data set entirely, do the feature engineering, clean the data set entirely, drop any of the variable. So at the end, we can apply the standard scaler just to get the means the data set which we are going to send to the model at the end, entire clean data set, we can use the standard scaler. So here I'm using the standard scaler for the entire data set because there above we are having a value of gender also 0, 1, then other values I'm having. So one is 0, 1, 0, 1, other values. So we can do it with the standard scaling. So all the data set can come into the standard scaling here. That is their standard scaler. Scale.fit underscore transform. Here I'm going to use it. The entire data set is scaled with the newer scaling. And here we can make the train test split with the scaled data. So all the data will be with the mean 0 and standard deviation 1 will be coming. So better results could be achieved. Then we can split it here, just like the normal work we are doing it here. Okay. So that we are doing it here. Entire code, the same codes I'm going to use it here. Matrix, you can check it out here. With the new data, you can do that. Even you can use the regularization, such as Ridge, Lasso, ElasticNet also, you can use that. These are the same code. You can use that. Lasso, Ridge, ElasticNet, you can use that to avoid underfitting or overfitting. So in this way, we do the ML, basic ML I'm talking about. Okay. So this is all overall for today. Thank you for the patience. Thank you very much. Thank you. Scaling can be used for any algorithm. Yes. Scaling is basically used just to scale the data before sending it to the model. So model needs the data set, and the data set which we are sending, that should be scaled. Okay. So in this way it is there. Correct. It could be any algorithm. Means that is a data set only. You are scaling the data set. Okay. So scale the data set and see whether your original data set is working well with the model, or a scaled data set is working well with a model, where you're getting the best prediction here. Okay, then thank you very much. Thank you.